All right, so we've been talking about empirical formulas. Empirical formulas are essentially an expression of the molar ratio of the atoms. Or in other words, C6H5S was the answer to this problem. So if I have C6H5S, what that's telling me, what this chemical formula is saying is 6 moles of carbon for every 1 unit, 5 moles of hydrogen, right? So 5. And then the 1 for that mole of sulfur for every unit. And then some stoichiometric statements that we could make. There's 1 mole of sulfur per every 5 mole of hydrogens, 6 moles of carbon for every 5 moles of hydrogens, right? 6 moles of carbon for every 1 mole of sulfur, right? Those are stoichiometric statements. This isn't 6 grams of carbon and 5 grams of hydrogen, right? It's a mole ratio. And empirical formulas or molecular formulas are all moles, expressing the amount of elements in terms of mole. Okay? Now, when we have a balanced equation, we know also that we can use the stoichiometry of that balanced equation, and it becomes very useful, right? Because if I know that, for example, this is the chemical reaction that I'm performing, I know that the amount of carbon monoxide here, CO, that I interact with oxygen in this reaction will produce the a specific amount of carbon dioxide. We see that 2 carbon monoxide go in and 2 carbon dioxides come out. So we see that that's a 2-to-2 or a 1-to-1 ratio. And again, that's moles of materials. I can also see that in this reaction, I consume 1 mole of oxygen gas for every 2 moles of carbon dioxide I make. So again, the coefficients, the numbers in front, the 2 here, the 1 that's not written there, and the 2 there, are values that allow us to make stoichiometric statements or stoichiometric comparisons. Okay, so here are some stoichiometric relationships for this chemical reaction in which 1 mole of nitrogen gas combines with 3 moles of hydrogen gas and yields 2 moles of NH3, which is called ammonia. And we say 1 mole of nitrogen goes in for every 3 moles of hydrogen that has to be consumed, right? So for every 1 mole of nitrogen that I'm going to react, I need 3 moles of hydrogen. For every 1 mole of nitrogen I react, I'm going to get 2 moles of ammonia, right? 3 moles of hydrogen consumed is going to result in 2 moles of ammonia. So all of these are stoichiometric relationships. And again, I'm saying moles, nothing about grams, right? These numbers, the coefficients there, are good for telling us the molar relationships, not the mass relationships. So here we go. We can answer a question like, how many moles of nitrogen gas are used when 2.3 moles of ammonia are produced? All right, so I can answer this question. I can say I'm looking for, to the right of the equal sign, moles of nitrogen gas. And they told me that 2.3 moles of ammonia were produced. So I can start here with 2.3 moles of NH3. And then I can go from moles of NH3 now to moles of nitrogen gas. And the ratio of nitrogen gas to ammonia is given in my equation here, right? Can you see the ratio? How many moles of nitrogen gas are there for every mole of ammonia in my equation up here?
1.
1 mole of nitrogen gas for every how many moles of ammonia? 2. Very good. So that shows me the math that has to be done. 2.3 moles of ammonia divided by the 2 will give me the moles of nitrogen gas. All right. Here's another scenario. If 0.575 moles of carbon dioxide is produced by the combustion of propane, so propane is C3H8, combustion means reacting with oxygen, right? It's just a fancy word for reacting with oxygen, burning, right? Another word we use for combustion. And we want to know if 0.575 moles of carbon dioxide, that's right here, the product, right, is produced by the combustion of propane, how many moles of oxygen must have been consumed? All right. So to the right of the equal sign, what are we going to put? What are we looking for?
Moles of oxygen.
Very good. Moles of oxygen. And to the left there, we can start with our moles of carbon dioxide, right? 0.575 moles of carbon dioxide. And then what goes down here?
Moles of carbon dioxide.
Very good. Moles of carbon dioxide. And I want to relate that to what?
To moles of oxygen.
Moles of oxygen. Great. Now, can you see what the molar ratio is between the moles of oxygen and moles of carbon dioxide?
Let's see. Moles of oxygen is 5. And it's 7. Well, wait. It's 7.
Where do you see the 7?
Oh, wait. Moles of 5 on the left.
Yep.
Then on the right, I'm adding the 3 and the 4 together.
Oh, no. All we're interested in is just moles of carbon dioxide is all.
Oh, moles of carbon.
Yeah.
Okay, right. Okay.
That's 4 moles of water. So if we wanted to know how many moles of water per mole of oxygen, that would be our 4 to 5. Or if they ask how many moles of product, because both of these are products, carbon dioxide and water, then it could be 7 here. But they're just asking for the carbon dioxide, so what's it going to be? The 3, right?
I was going to say 3.
The 3
okay.
in front of the carbon dioxide. All right, very good. So our 0.575 times the 5 divided by our 3, and that's how we can identify how many moles of oxygen must have been consumed based on the amount of carbon dioxide that was produced in the process. Okay, so here's another one. How many, this time not asking about moles, but this time asking about grams. How many grams of aluminum oxide are produced when 41.5 grams of aluminum react? Okay, so to the right of the equal sign, we don't want to confuse ourselves. We try to take this into little pieces, understandable, digestible bits. So I just am going to write what they're after, and it says right there how many grams of Al2O3, that's aluminum oxide.
Okay.
So grams of aluminum oxide, and can you see what we can start with at the top left there?
41.5 grams of Al.
Of aluminum. Very good. Grams of aluminum. Great. So now I know the grams of aluminum has to go down there. And, this is, hopefully most of this was without brain cells, but where do we go now? What are we going to try to get to? Well, we need to be able to use that equation, right? Because that equation relates the aluminum to the aluminum oxide. The coefficients, the stoichiometry, right? We need to be able to relate that. So how are we going to do it? How are we going to relate that? We're going to have to...
do we multiply 2 times the 26 point...
Okay.
985.
26.985. We need that to go to moles.
Or is
We
that
need to go to moles, right?
okay? Okay.
Right? So we need to convert the
Okay.
grams to moles.
So then it's just 2, right?
It's what?
It would be 2 moles.
Well, no, here
Top.
we're looking at how many grams of aluminum are there per mole of aluminum, and it's the 26.985, right?
Oh, I see. Okay, so it's
But
yeah, it's 26 would go
that's
down
right,
below, right?
26.985. Whoops.
Now that's
For every one mole,
right?
That's right.
Okay.
Okay, now we're in moles of aluminum, and we want to go to what? Well,
To the
eventually.
grams.
So we're going to go to moles of
Okay.
aluminum, Al2O3, aluminum oxide, because that's what the equation can tell me.
Right.
It allows me to go from moles of one material to moles of another, and then I can go from moles of aluminum oxide to grams of aluminum oxide. Okay? So, the molar ratio. What is the molar ratio between moles of aluminum and moles of aluminum oxide in our equation?
So that's just
One meaning what?
1
over
over
1,
1, right?
So we can look right here and find the aluminum oxide. Here's the aluminum oxide. It has a 1 in front of it.
Right.
And then we find the aluminum, but it has a...
Oh, we're adding
Well,
that too?
that's down here. This is moles of aluminum, right? So I'm relating
I
moles
see.
of aluminum to
yeah.
moles of aluminum oxide. Very,
All right.
so then we got
okay.
1,
Yeah. So
1 over 2. Very good. 1 over 2. Okay. Now, what is this business saying? Grams of aluminum oxide per mole of aluminum oxide?
Yeah, that's what
Yeah,
it's
so
saying,
what
huh?
number goes in there?
Well, we know our grams is the 26.
That's for aluminum.
Oh, yeah, this is the
Yep,
whole
but we
thing,
have it
right?
here on the slide.
Oh, it's
Yeah.
right there, huh? Oh, 101.
So,
Okay.
about 102, so I'll round it up to 102 grams for every
Okay.
mole of aluminum oxide. Okay, so 41.5 divided by the 26 divided by 2 times the 102, and that'll give us 78.4 grams of aluminum oxide.
Can you pause
Yeah.
for...
Okay, let's try another one using this same equation here, okay? This time, I'm going to write down the question here, okay? So essentially, all we're using is that same equation. And I'm going to say, how many grams of how many grams of aluminum do we need to produce 3,000 grams of iron? Now, this is a fine question to ask here, because this chemical reaction here is a reaction that they use to weld railroad ties together, right? They bring the railroad ties close to each other. They put in a mixture of aluminum and iron oxide together, and then they light it on fire, and this reaction occurs and results in molten iron. And the molten iron will cool and leave behind iron in between those two railroad ties, and then they can just kind of sand it to the shape that they want to. All right, so if I know that the volume between two railroad ties is about 3,000 grams, then I need to know how much aluminum I need to put in to make sure I get the appropriate mixture, right? So How many grams of aluminum do we need if we want to produce 3,000 grams of iron? So what would go to the right of my equal sign here?
3,000 grams of iron.
Well, over here to the right, what am I after?
And then we're after how many?
This is the 3,000 grams of iron, right? And what are we looking for over here?
Oh, I see. Okay. I was doing it backwards, I guess. So the AL is AL in grams.
Yeah, that's what we don't know. How many grams of aluminum? So that goes to the right of my equal sign. Very good. So if I have 3,000 grams of iron needed, how many grams of aluminum do I have to start off with, right? That's what this is going to tell us. So I go from grams of iron to what? I always want to...
wait. Does it give us any...
oh, it doesn't...
That's all the information we have, right?
Yeah, it doesn't give any information for the iron. Here, we have to pull up our periodic table. Let's see if we can see it on there. There's iron. It says 55.847. 55.847. Now, how are we going to use that 55.847? That's grams per mole, right? That's
grams per mole.
Grams of iron per mole of iron. So when we start with grams, we always want to go to the land of the moles, we say, right?
That's
go
right.
to the land of the moles. And the reason we want to go to moles is because there we can take advantage of this equation, because this equation is an expression of the different reactants and products in terms of moles, right? So if I go from grams of iron to moles of iron, then I can go from moles of iron to, where do I want to go to?
To then grams of AL.
Well, I can't go directly to grams.
Oh, wait. I'm sorry. What does that say? Moles of iron?
Yeah, moles of iron down here.
Okay.
And I want to go to moles of aluminum up here. Right?
All right.
Because that's what I can do with the equation here. I can go from moles to moles. Moles of one material to moles of any other material. Okay. So after I'm in moles of iron, I can go from, aluminum. I can go from moles of aluminum now to grams of aluminum.
Okay.
So let's see if we can fill the values in here.
Okay.
What are the numbers for this first one here?
Okay, so 1 mole would be the 55.8. Well, we could just say 58, right?
55.8. It's fine. Yeah. Great.
Okay. Now we're going to go from moles of iron down below. So that would be 1.
Moles of iron 1.
Well, let me think this. Sometimes yeah.
Okay.
Well, let me think how this is going to work. And then moles of
iron to moles of aluminum. How do I get that relationship? It's from the equation, right?
Okay, I'm lost.
Up here in the equation. Can you see the equation, or is it a little too small?
Oh, wait. Okay. So we can reference this equation. Yeah, grams to mole down below the mm.
No, over here, right here. This equation right here.
Oh, okay.
It tells me the ratio of moles to moles. For all my reactants and all my products, I can always use the coefficients to tell me the mole-to-mole ratio of the different reactants or products, elements, whatever they are. So I can use the coefficients on my iron and the coefficients on my aluminum and put them here in this conversion factor.
Okay, so yeah, 2 to 2.
Very good. 2 to 2. That's right. 2 to 2. Now, how do I get from moles of aluminum to grams of aluminum?
So now we look at the weight
Mm-hmm.
for aluminum,
Mm-hmm.
and well, it's down below there
Uh-huh.
too. So it's 27
That's right.
grams.
Mm-hmm. So 27 grams for every 1 mole.
Okay.
So, calculator, 3,000 divided by 55.8 times 2 divided by 2 times 27.
Oh, so you went 3,000, then you went ahead and divided.
Yes, up on top.
So do you get the same answer if you just went ahead and multiplied all the top and then
Yes.
divided by the
Yes. It doesn't.
sum of all the bottom?
Yep, it doesn't. Not the sum, but the you just divide by whatever's on the bottom. So you take the top
Right.
number, divide by that, divide by this, divide by that, times by that, times by that. It doesn't matter the order that you do that.
Okay, so you could go 3,000 times 2 times 27 for the top.
Yep, and then divide by 55.8, divide by 2.
Oh, I see. Okay. Gotcha.
Okay, good. So here is another question for us. All right, so how many moles of KOH? Do you want to try to help me name that compound? What's KOH?
KO. Where am I looking at?
Right here. How many moles of KOH?
Okay. Okay.
What's the name of that thing?
Yeah, what's the name of that?
K is element 19.
Okay, it's okay. Just a second. Okay. Oh, potassium.
Yep, potassium. And now OH, that's a polyatomic ion, right?
I knew there'd be a polyatomic ion. Okay, OH. And that's hydroxide.
Very good. Excellent. So we got potassium hydroxide. Potassium hydroxide. So how many moles of potassium hydroxide are required to make 3 moles of, what's this compound called?
Potassium. Okay.
So
yeah, I know it's
polyatomic ion.
Yep. Sulfate.
Very good. Potassium sulfate. Excellent. Let's just do a quick little review on potassium sulfate. K2SO4,
Okay.
right? Whoops.
Okay.
K2SO4. This is potassium sulfate. And the things we need to remember whenever we think about potassium or whenever we think about an ionic compound is the ions that it's made of. So it's made of 2 potassiums and 1 SO4. And we can look on the periodic table and see that the SO4 is a 2 minus. We can look on the back of our periodic table, polyatomic ion chart. So then the potassiums have to have what kind of a charge? And there's a couple ways we can see that.
Yeah, positive
one. We can look on the periodic table, but we can also see that we need to have these 2 balanced. So,
right.
Okay, excellent. So how many moles of potassium hydroxide are required to make 3 moles of potassium sulfate? How many moles of potassium hydroxide? So to the right of the equal sign, what goes to the right of the equal sign?
Moles of KOH.
Very good. Moles of potassium hydroxide. And then what goes to my top left?
It'll be the 3 moles of K2SO4.
Very good. Potassium sulfate. Excellent. All right. And then, can I get from moles of potassium sulfate to moles of KOH?
Yeah.
What is that ratio and how can I tell?
Okay. So we look at the equation.
That's right.
And moles of KOH, we see that there's 2. And then moles of K2SO4, we see there's 1.
Very good. So if we do the math here, how many moles of KOH should we be able to get if we have 3 moles of K2SO4?
So we should have 6.
That's right, 6 moles. And that's our answer. Wonderful job.
Now, so the moles of K2SO4 cancels with the moles of K2SO4 down below,
That's
right?
right.
So now we're looking at 6, the answer, right? 6
moles of potassium hydroxide, KOH.
All right.
Good. Good work.
So there was a question I have, but let's see, maybe pause for a second.
Okay. Now, here's another problem for us to practice. All right. Given the reaction, so that nice chemical reaction, it's so nice when they give us a chemical reaction because it is magic, right? It's got so much power in it. It tells us the molar ratio of the different reactants and products. So given that reaction, and then the question is how many grams of water would result from the complete reaction of 1.2 grams of H2SO4. All right. So what goes to the right of our equal sign? What's our unknown?
The grams of H2O.
Grams of water. That's right. Grams of H2O. What do we start with? Top left?
The 1.2 grams of H2SO4.
Very good. 1.2 grams of H2SO4. All right. Help me out. Where am I going to go?
So right there, we'll write H2SO4.
We got to write grams, right?
Grams,
H2SO4. Right. Good.
Okay, now let me look at this equation again.
We want to go to what? First, let's decide where we want to go.
Okay.
We want to go to moles because if we get to moles,
that's right. We got to go to the land of the moles.
That's right. To get the power of the equation. That's what you do in the land of the moles. H2SO4. All right, so moles of H2SO4. And then down here, I'm going to get what?
Yeah, moles of H2SO4.
Very good. And now I have to get 2 moles of what?
Of the water. Well,
that's right. Moles of the water, right?
Okay.
That's what the equation can give me. And then I can go from moles of water to the grams. That's right, grams of water. Okay, so let's go back and fill these values in now.
Okay.
What is the value that's going to go here?
1.
1 what? Mole? How many grams of H2SO4 are there per every mole? On the on this number here, or on this chart, or on this question, sorry, it says it has them in parentheses here. See how it's 98.08?
Oh yeah.
That's telling us the molar mass. So, all right, so there we go. So we got the molar mass of H2SO4 being 98. So that's how many grams there are per mole. So I'm going to write in here 98 grams per mole. Okay, so what about this? Where is my molar ratio going to be? How am I going to get that? Oh, wait, this isn't the right one. This isn't the problem we're on. Whoops, is it?
Yeah.
Oh, yeah,
I
it
thought
is.
was.
Yeah, it is. Yeah, it is. Okay. Grams of water. So 98 grams of H2SO4. So how do I get from moles of H2SO4 to moles of water? How do I do that?
Okay. So we're looking at the equation,
Yeah.
and we see that it's well, okay, 2, right?
2 moles of water, right?
Yeah,
To what?
2 to 1.
To 1 mole of H2SO4. Good. Now how do I get the grams of water per
Now
mole?
that mole below, that should be a K, right?
Which one?
It looks like you have H2SO4.
Down here?
Well, it is H2SO4, isn't it?
Yeah. Mom, do you want to get the boys? The boys?
So Dan, when you look on top, given the reaction, right?
Yeah.
You see that product is 2H2O plus K2SO4.
Yes. So we're going to be making some potassium sulfate here, K2SO4, but the question doesn't ask anything about
But
that.
the question doesn't ask anything, huh? It's asking
Just about how many grams of water.
1.2 grams of H2SO4. Okay. Okay, I was looking at focusing on the wrong part of the equation there.
All right.
So we really don't need that top equation.
Yeah, we do, because that gave us the molar ratio of 2 moles of water to 1 mole of H2SO4, right? 1 in front of the H2SO4 and 2 in front of the water. Right?
Gotcha. Okay.
Good. Now, where do I get this? Where do I get this grams of water per mole of water?
So we have the mass
Yep.
of 18.
18. 18 grams for every 1 mole. Very good. So I'll leave the calculator up to you folks at home, but multiplying that out should give us 0.44 grams. 0.44 grams. Okay, excellent job. Clearly, we see that it's important to have a balanced equation if we're going to be able to solve these types of problems, right? And we had a discussion previously about how to balance equations. The main thing we want to remember, this is kind of a review because we paid close attention to it last time we visited it, but we revisit it in this chapter as well in the book, and so we mention it again here. But we're not going to spend as much time balancing equations because we feel like we've had that practice. But if you haven't, these are some good opportunities to practice. So if you want to have time practicing, we're not going to go over that now, but this would be a chance to push pause and then look. And remember, you make a list of the elements on both sides, count them up. If they're in polyatomic ion groups, then pay attention to that. Use those groups to help you. So I'm going to show you the answers here in 2 seconds. 1, 2. All right, so hopefully you knew how to balance that one. Try this one too. I'm going to show you the answer. Push pause if you don't have the answer yet. 1, 2. Okay, good. And then one last one. All right, so push pause to balance it yourself. And then 1, 2. Here's the answer. Okay, very good. So this is the last little practice here as well. And again, why we need to make sure we know how to balance the equation, because if we don't have a balanced equation, we can't answer any problems about anything, right? If we don't know what the ratio of reactants to products is, then we just are blind. We don't know what we're doing. Okay, so the answer to this one I'll show you real quick. If you haven't got a chance to do it, now good time to push pause, but here it goes, 1, 2. So it's 2. That's the coefficient in front of the KCl when this is balanced. All right, so now I'm going to introduce to you a topic concept called limiting reagent. Limiting reagent. Now, you guys are familiar with this topic. We don't call it limiting reagent when we're making sandwiches, but you know all about it because frequently in your life, you've gone to the cupboard to make yourself a peanut butter and jelly sandwich, and you get out the peanut butter and you have a half a jar. You get out the jelly, you have a whole jar. And then you go to get the bread, but you only have one slice of bread, right? How many sandwiches can you make if you have lots of peanut butter, lots of jelly, but one slice of bread? And, you know, you can say, oh, I can make a half a sandwich, but you can't make a sandwich, right? You don't get a sandwich unless you have 2 slices of bread. And so you'd say the bread is limiting the reaction or the process there. So the bread is the limiting reagent. Reagent just means chemical or material. All right? So when 2 materials react together in a chemical reaction, like nitrogen and hydrogen coming together to form ammonia in this reaction, if you have a lot of one, like if I have 16 hydrogens, for example, and I have 1 nitrogen, even though I have extra hydrogen, that 1 nitrogen is going to limit the number of ammonia that I can get. Okay? And the way that we determine this, the way that we find the limiting reagent, is we need to solve the answer for how much we're going to get for the 2 different amounts separately. Okay? And you kind of recognize this previously in that last reaction. We weren't talking about one of the products at all, the potassium sulfate. And we weren't talking about the potassium hydroxide, the other reactant, right? We just said, if I had this much H2SO4, how much water would I get, right? Well, if you have H2SO4, you're not going to get any water. You need to have the potassium hydroxide with the H2SO4 to get the water, right? But we weren't ever talking about that. We were just assuming that we had plenty of the other stuff. So, if I wanted to do this reaction, I said, how much ammonia, NH3, will be produced? How much ammonia will be produced if 1 mole of nitrogen N2 reacts? So this is the same type of question previous, like we were doing before. How many moles of ammonia will be produced if 1 mole of nitrogen reacts? Well, we can answer that question pretty good because we got some practice and we can look at our equation here. If I put 1 mole of ammonia in, 1 mole of nitrogen in, how many moles of ammonia am I going to get out? Can you see? 2. That's right. How much ammonia will be produced if 1 mole of nitrogen reacts? 2. But if I say, how much ammonia will be produced if 1 mole of nitrogen reacts with 1 mole of hydrogen? All right. So now I have information not just about one of the reactants, but I have information about the second reactant as well. How much ammonia will be produced if 1 mole of nitrogen reacts with 1 mole of hydrogen? Okay. So now I have to look at this and say, we knew the moles of ammonia, NH3, for every 1 mole of nitrogen gas. right? Because we said that to get to moles of ammonia from moles of nitrogen gas, it's a 2-to-1 ratio, right? That's basically how you answered that question, right? However, now if we're saying we're only going to get 1 mole of hydrogen, 1 mole of hydrogen, then the answer here is 2. If I get 1 mole of hydrogen, how many moles of ammonia, NH3, am I going to be able to get? I need to go from moles of hydrogen to moles of NH3. Can you see the molar ratio in my equation? What's the ratio here?
3 on top.
3 for the ammonia? Well,
Yeah.
there's the 2 in
Right.
front of the ammonia there. See that?
Oh, I mean,
2
yeah, that's
here,
right,
and then
two.
the 3 is on the bottom, right? Because this is the moles of the hydrogen.
Right.
So 1 times 2 divided by 3, I'm only going to be able to get 2/3 of a mole of ammonia. Okay? So, basically, if I put in 1 mole of hydrogen gas, I'm only going to get 2/3 moles of ammonia out. Because the reaction says, and you can see the reaction there, right? It says it requires 3 moles of hydrogen to get 2 moles of ammonia. So if I only put 1 mole of hydrogen in, I'm only going to get 2/3 moles of ammonia. However, if I put in 1 mole of nitrogen gas, I'm going to get 2 moles of ammonia out. But both of these statements can't be true, right? Both of these can't, they're both true, but in the question, it's asking, what if I react 1 mole of this with 1 mole of that? Well, that's fine, but one of them is going to run out before the other one is completely used up, right? And I can tell that it's the hydrogen that's going to run out because it has the smallest amount of product. The smallest amount of product, right? So that makes hydrogen the limiting reagent. And it makes this value here what we call the theoretical yield. Theoretically, this is how much I should be able to get. Why can't I get 2 moles of ammonia? Why am I not going to get 2 moles of ammonia?
Well, limited.
Yeah, what's going to
agent.
run out? The
hydrogen. Well, wait.
The hydrogen.
Yeah.
Yeah, the hydrogen is
thing.
going to run out.
Right.
So this tells me how much I theoretically could get if I had excess nitrogen. This one tells me how much I could get if I had excess hydrogen. And then I look at the 2 answers, find out which one's the smallest, recognize that that's the limiting reagent, and know that my hydrogen is going to run out. So I'm going to have extra nitrogen in the end. Okay, very good. So let's look at this one and see if we can determine what our limiting reagent is and what our theoretical yield is. And for this, they're asking the limiting reagent and theoretical yield for water. Now, it's very nice of them, and I don't think any time in an exam are they going to ever say, what is the limiting reagent, right? Because the real issue with limiting reagents is recognizing as a student or as somebody performing the chemistry that you are going to have one of your chemicals as a limiting reagent. It's going to run out, and so the other one isn't going to be able to be consumed at all. All right? So it's nice that they've asked for the limiting reagent, but usually they're just going to ask the question, and you're going to have to know it's a limiting reagent question. And here's how you can tell. Here's how you can tell it's a limiting reagent question. Before, the questions before, when we never had introduced the limiting reagent, were always something like, if I have 1 gram of this reactant, how much product do I need or get? Or if I have 1 gram of this reactant, how much of the other reactant do I need, right? But in a limiting reagent problem, they always say, if I have this much of this reactant and this much of the other reactant, right? Because now they're telling you amounts of two different reactants. So that's indication that it's a limiting reagent problem, okay? And you know, gradually you can kind of recognize that because you think, wait a second. If they told me I have a certain amount of both of those, then one's going to run out. Which one is it? And how am I going to figure that out? And that's what limiting reagent problems allow us to know which one is going to run out. So I have to find out the grams of water. That's what they're asking me here. And because they asked me, hey, 1 gram of each reactant, I can say, aha, limiting reagent problem. And so I'm going to write it down twice. I'm going to write down and identify the mass of water twice. The first time with 1 gram of one of the reactants, and the second time with 1 gram of the other reactant. So which one do you want to start off with on top? Maybe we should name this compound. What's this compound? CaOH2.
Okay, calcium.
Mm-hmm.
Let me look at OH. I guess it's on the back.
Very good.
Hydroxide.
Calcium hydroxide. Calcium hydroxide. Should we start with 1 gram of calcium hydroxide here?
Okay.
Okay, 1 gram of calcium hydroxide. So how am I going to get to grams of water?
Well,
Where do I go?
yeah,
To the moles. That's
to the
right.
moles.
I go to moles of calcium hydroxide. Okay. After I get the moles of calcium hydroxide, where am I going to try to go?
Okay, now we're going to go up to the moles of
Very good.
H2O.
Moles of water. All right. And then I go from moles of water to
To the
grams
grams of water.
Very good. Okay. So what are my values? Can you see them down there? Is it a little too small?
There we go. Okay. So CaO2 is
74 goes on the
74.
bottom here with the grams. 74 grams for every mole. Very good. What about my molar ratio? Where am I going to get that?
okay. We have yeah, where do you get that?
That's our equation, right?
Okay, so we got the grams.
Hmm?
Now we're 18
For the water over here? Yeah, 18 grams
For
for
the
every
water.
mole.
That's over there.
Yeah.
And then
What
I'm
about
jumping.
moles? Yeah.
Yeah, the molar's
Yeah.
throwing me off. Okay,
This
I'm
is-
lost.
Oh wait, we're looking at the equation then.
Oh
That's
wait,
right.
we're looking
Uh-huh.
at the equation then, right?
Yeah.
But up on
So we
top.
see that we're looking
So we
at
see
the
that
product.
we're looking at the product here.
We see that
Well, what are
So
we
we
looking?
see
You have to
that,
look. You have to read my bad handwriting here. Can you see what I've written here in these boxes?
mole of H2O on top.
Mole of
Yep,
H2O
moles of water on top.
right?
And then what's up on? Okay.
And
That's
then
the
what's
calcium
on
hydroxide.
Okay, and then
So
2 moles
Mhm.
of H2O, right?
And 1 mole of
And 1 mole
Very
of
good.
calcium
Excellent job.
hydroxide.
So let me try to figure this out. 1 divided by the 74 times the 2 times the 18. I'm getting 0.486 grams of water. Very good. So the bottom one here, what are we going to use there? Grams of what?
HCl.
Very good. HCl.
HCl.
Grams of HCl. Going from grams of HCl to where?
To the
Moles
moles on
of
moles
HCl.
on top.
Wonderful. And then from moles of HCl to what?
to the mole of
Whoops.
oh, okay.
Oh, okay.
So yeah, mole of H2O.
So
Yes,
yeah,
water.
mole of H2O.
And then from moles of water to grams of water.
To-
Okay. What about this? What's grams of HCl to moles of HCl? What values go there?
Okay, so we look down below.
Okay, so we look down below and
HCl's 36.
HCl
Yeah,
is
36.5 about. And then 1 mole of HCl.
Okay.
All right. Where do I get this ratio? The moles of HCl to moles of water.
From the equation.
Okay.
Okay, from the equation.
So we have
So we have 2 HCl
Mm-hmm.
down below, yeah. And then we have
water.
Very good.
2 of water.
Then we have
Then we have
guess we'll keep the 2 of
I guess we'll keep the 2 of
No,
water
this one
down
isn't
below,
the equation
right?
here. This is just how many grams per mole, right?
oh, okay, so 1 mole of
Yep.
Oh, okay, so 1 mole of H2O.
And how many grams are there
Okay.
in 1 mole?
grams
And
is
grams is
18.
yeah, 18.
All right, I'm going to do the calculations here. 1 divided by 36.5 times 2 divided by the 2, and then times the 18. Okay, 0.493, 0.493. All right, so what does that tell us? We did it twice, and what have we learned?
Or
Yes.
limiting, well,
Limiting
What's the
reagent. What is
term?
the limiting reagent?
okay. And that would be the carbon, I forgot what we called it, the
CaOH here?
CaOH.
The calcium hydroxide?
yeah, there's less of that.
Yeah.
Very good.
there's
That's the
less of
limiting
that,
reagent.
right?
Can we get 0.493 grams of water? No, we can't do it. We can't get that much water, right? Because we're going to run out of calcium hydroxide. So, what do we call this? We call that the
Theoretical yield.
very good
Theoretical yield.
So calcium hydroxide is our limiting reagent, and 0.486 grams of water is our theoretical yield. Okay, fabulous job. The limiting reagent scenario required us to do it twice, right? Okay, here's one more. Another chance to practice our limiting reagent understanding. How many grams of NO can form when 30 grams of ammonia and 40 grams of oxygen react according to this reaction? Okay, so we've set it up twice, right? And what goes to the right of the equal sign?
Okay.
Well, we're looking at
Well, we're looking at
so the 2 elements we're
so
looking
the
at,
the
right,
2
on the
elements
left
we're looking at right on the left
is
is
NH3 and then
NH3 and then
Yes.
O2, right? Those are the 2 we're looking at.
and then
Where are we trying to
And
go, though?
then,
Let's make sure we
how
don't forget
many
to put our...
grams of NO
How many grams of
Very
NO?
good.
So I guess NO is
That's
on
right.
the right.
Excellent job. Now, I forgot to let you tell us, but tell us, how did we know, or how can we tell that we had to do it twice? It doesn't say what's the limiting reactant. How did we know we had to do it twice?
because of the and.
Because of the
Yeah.
and.
It gave us information about amounts of 2 different reactants, more than one reactant. Great. Okay, So grams of NH3 to what? To moles of NH3.
To moles.
Moles of NH3 to what?
To moles of
NO.
NO.
Moles of NO to grams of
Grams
NO.
of
Very
NO.
good. Want to help me fill in these numbers?
Okay. Yeah, this is where gets iffy. So we look below, we see grams of NH3 is
Very
17.
good. 17 grams for every 1 mole of NH3. Excellent.
And then we have below 1 mole of NH
Moles of
NH3.
NH3.
Yeah. To 1 mole of
Okay.
NO.
Now,
No, wait, that can't be right. Now we got to look at our
Yeah.
equation up there, right? So our equation of
Okay.
NO is 4. And
Very
NH3
good.
is also 4. So I guess that is
it worked out. You
1-to-1
got lucky
ratio,
on that one.
right? Yeah. And then we look at mole of NO. So that's 4. Grams of NO is 30. Okay, I would send 4 of NO. Am I wrong? Oh yeah, because it's 30 grams to 1 mole. Is that how that works? Because I keep looking at that equation that says 4 NO, right? Oh, I can't hear you. I'm sorry.
So here, we're relating moles of NO
Oh, this is where we go 4. Okay.
to moles of NH3. But here, we're just wondering how many grams of NO is in a mole of NO. If you wanted to put a 4 here, you're asking how many grams of NO are in 4 moles of NO. And so then you'd have to take that 30 and multiply it by 4, right?
Oh, I see. So the weight down below, well, yeah, that's a molecular mass.
That's right. That's how many grams there are for 1 mole of those materials.
For 1 mole, yeah. Okay, gotcha.
All right, now what number goes here?
Yeah, we got, let's see. So that's in grams. So we're NH3, it says is 17.
17? Oh, that's how many grams there are per mole. But for this one here, I'm trying to figure out how many grams of NO I can get by putting in.
Wait. Well, I'm sorry. You're asking me how many grams of NH3, right?
Yeah.
And okay. So now I need to look at the equation.
Well, we just need to read the problem. It says how many grams of NO can form when 30 grams of NH3. So this is where 30 grams of NH3 comes in.
Okay.
Okay. Very good. Now, let's do the grams of oxygen to grams of NO.
Okay. So before I get distracted, let's put in 40.
Okay, yeah. 40 grams of oxygen. Good.
Okay, then below we'll put in to the moles.
What?
Okay, and so we have 1 mole per grams of oxygen, so that's 32.
Very good. 32 of grams of oxygen gas. Very good. And then I go from moles of gas to
moles of
NO.
NO.
Right. Yeah. Okay. How many? What's the ratio there?
Okay. So 5 moles of oh wait, let's see. Yeah, 5 moles of O2.
Okay.
Oxygen, I mean. And then NO of 4 moles of NO.
Very good.
Okay, and now we have one more
Mm-hmm.
and now we have moles and then grams of NO.
Okay.
Okay, so now our
Calculator time, right?
now that 30 grams
This last one here?
of NO we're getting from the bottom, right?
That's right. Sorry, I should have let you do that one. That's grams
No,
per mole.
No. Yeah.
So let me do the top one here. 30 divided by the 17 times 4 divided by 4 times 30. So I'm getting 52.95. And then the bottom one, 40 divided by 32 times 4 divided by 5 times 30. And that's giving me 30 grams of NO.
Wow.
So, how many grams of NO am I actually going to be able to get?
30.
30 grams of NO, meaning that which one is my limiting reagent? The oxygen gas. Very good. So the answer is 30 grams of NO because, and that's all they asked. They didn't ask me what the limiting reagent was. They didn't even tell me it was a limiting reagent problem. But because we knew information about 2 of the different amounts of reactant, we knew that it was going to be a limiting reagent problem. Okay, very good. There's just a couple more slides, but we could probably do them next time. Is that okay, or what?
Yeah, that's fine. Whoever you want.
Well, I don't know. Do you have a little bit of time? Do you want to keep going? There's only 2 more slides.
I got some
Okay,
time.
the easy concept. It's
You're going to explain to me. Are we taping?
So this one is pretty straightforward. This idea of what we call actual yield. You probably already know about this, just the term actual compared to theoretical. But we experience it when we make cookies, right? You make some cookie dough and the recipe says this will make 36 cookies. But in the end, you only get 24 cookies, all right? And that means your actual yield was the 24, whereas theoretically, they said you should be able to get 36. This happens in chemistry also because, well, there's a lot of reasons why. When you react, sometimes the products get stuck to the container and you can't scrape them off. Sometimes you get byproducts, so the reaction didn't occur exactly perfectly. Sometimes the reaction just stops occurring, and so your reactants aren't all consumed, right? So we have a lot of different things that can happen that can actually change what we call our actual yield, all right? So the actual yield is what we get, whereas the theoretical yield is how much we were thinking we should have been able to get. And then our percent yield is our actual yield divided by the theoretical yield times 100. So for example, if I made that recipe of cookies and I only got 24 cookies, I could take the 24 divided by the 36 times it by 100 to make it a percent. And that would give me my percent yield. Right? Follow that?
Yeah.
So here's an example of a problem. When 6.4 grams of CH3OH, that's methanol, is mixed with 10.2 grams of oxygen gas and ignited, combustion, 6.12 grams of carbon dioxide was obtained. What was the percent yield of the carbon dioxide? What was the percent yield of the carbon dioxide? And this is also a limiting reagent problem because it's telling us 10.2 grams of oxygen gas and 6.12 grams of carbon dioxide. All right. So I'm going to let those watching at home to identify how many grams of carbon dioxide they expect. If we take the 10.2 grams of oxygen, can you tell me how many grams of carbon dioxide I would expect? And then do it a second time, take the 6.4 grams of methanol, CH3OH, and tell me how many grams of carbon dioxide I would expect. All right. Then we find the one that's the lowest value, and that lowest value should be our theoretical yield. Okay. So, if you haven't done that yet, take the time to do it now. All right. So hopefully you did it. I'm going to show you how to do it now. We're looking for our grams of carbon dioxide, starting with 6.4 grams of CH3OH, going from grams of CH3OH to moles of CH3OH, and then moles of CH3OH to moles of carbon dioxide, and then moles of carbon dioxide to grams of carbon dioxide. There's 44 grams per mole. I can look at the equation and see that 2 CH3OHs go in and 2 carbon dioxides come out. So that's a 2-to-2 ratio there. And I can also look and see that the molar mass of the CH3OH is 32. So 1 mole is 32.04 grams. All right. I put that in my calculator. 6.4 divided by 32 times 2 divided by 2 times 44. That's 8.8 grams of carbon dioxide. All right. So we're going to do that again, this time with our 10.2 grams of oxygen. 10.2 grams of oxygen gas, and we're wondering how many grams of carbon dioxide that's going to be able to produce. I go from grams of O2, 32 grams for every 1 mole of O2, and then I go from mole of O2 to mole of carbon dioxide. And look at my numbers up there. 3 moles of carbon dioxide for every 2 moles. 2 moles of carbon dioxide for every 3 moles of oxygen gas, right? That's what my equation tells me there. And then I go from moles of carbon dioxide to grams of carbon dioxide. And there's 44 grams for every 1 mole. Calculator, 10.2 divided by 32 times 2 divided by 3 times 44. That's 9.35. Okay, so what do those values tell us, Walt?
That our limiting agent is the I can't quite read that. I can't quite read that.
CH3OH.
The bottom one.
Yeah.
The bottom one.
The methanol. Yeah. The methanol. Very good. And this 8.8 then is what?
So we're going to divide 8.8 by 9.35.
Oh, not the 9.35.
Not that. No. Not that. No. By
6.12. Right?
That's our actual, isn't it? That's our
right
actual,
here, yeah.
Isn't it?
6.12 is our actual.
Okay. 6.12 is our actual.
6.12
is our actual. So that can be divided by our
yeah,
theoretical.
6.12 divided by our, what we got down here, which was what, 8.8?
Yeah.
Times 100, 69.5%, 69.6%. Okay, very good. So that's how we get our theoretical yield. All right, very good job. Thank you so much for hanging in there for the last little bit.